Hello, ma'am. Am I audible?
Yes, Rose. Yes.
Okay. Honorable dignitaries, learned delegates, respected teachers and students, a warm good evening to one and all. Welcome to the instructional workshop on advanced cryptography organized by the Department of Mathematics, St. Thomas College, Thrissur in association with DRDO and CRSI. Cryptography is the art of keeping information secret and safe by transforming it into a form that an intended recipient cannot understand. This workshop is aimed at an introduction to modern cryptography, and what follows will be a mix of applied and theoretical cryptography. Our financial partner is DRDO, the R&D wing of Ministry of Defense, Government of India, whose vision is to empower India with cutting-edge defense technology and a mission to achieve self-reliance in critical defense technology and system. Academic support is extended to this workshop by CRSI, the Cryptology Research Society of India, which is a scientific assembly consisting of academics, researchers, specialists, students, and institutions interested in promoting the science and technology of cryptology, data security, and allied disciplines in India. Let us begin our 4-day workshop with blessing from Almighty. I request you all to join me in a moment of silent prayer to seek blessing from the Almighty. Okay. I invite Dr. Shaju M.I., the head of the department and assistant professor at the Department of Mathematics, St. Thomas College, for the welcome speech.
Okay, good evening, everyone. Respected Principal of our college, Dr. Father Martin K.A., Vice Principal, Dr. Father Anil George Kongoth, today's resource person, Dr. Tony Thomas, Program Coordinator, Dr. VGM, my dear colleagues, research colleagues, and students. It's my pleasure to welcome you all for instructional workshop on advanced cryptography, IWAC 2023. The Department of Maths, St. Thomas College, Thrissur, is on its 97th year of affiliation. We have two UG programs, BSc Maths with Physics and other is BSc Maths with the Computer Science. And our PG program, MSc Maths with electives, Cryptography and Fluid Dynamics. Our department has been a research center since 2016 with more than 15 research scholars and 4 research guides. Our main areas of research are cryptography and fluid dynamics. We also conduct certificate programs, value-added courses beyond the syllabus for students of our department, other departments of our college. We conduct online and offline, international and national workshop and seminar every year. IWAC 2023 is a 4-day workshop conducted by online mode with the first section scheduled from 5:30 to 7 p.m. and the second section from 7:30 to 9 p.m. every day. Now moving on to the duty entrusted on me. First of all, I welcome our principal, Dr. Father Martin K.A. He has been supporting us for all the activities of our department, as he has to attend an urgent meeting. In his absence, I heartily welcome Dr. Father Martin K.A. to this workshop. Our Vice Principal, Dr. Father Anil George Kongoth, is here with us. Under the guidance of Dr. Father Anil George Kongoth, our college got NAC A grade, a double plus grade with 3.7. He is a faculty of computer science. On behalf of all, I welcome Dr. Father Anil George Kongoth to this program. Today's first section, handled by Dr. Tony Thomas on the topic, the quantum threat to cryptography. Dr. Tony Thomas is Associate Dean and Associate Professor at the Digital University of Kerala. On behalf of all present here, I welcome Dr. Tony Thomas sir to this event. Our Vice Principals, other principals, Dr. Sister Alphonse Matthew here. I welcome Dr. Sister Alphonse Matthew to this program. Next, we have Dr. Vijayam, the program coordinator. She is the backbone of this program. She is one of our research guide, and her research areas are algebra and cryptography. I welcome Dr. Vijayam to this event. Now I welcome our Bursar and Executive Manager, Father Biju Padangadan, other Vice Principals, Dr. E.D. John, Dr. V.M. Chako, my colleagues, faculties of other colleges, research college, students, Jinsi Poli, student convener of this program, and all participants of this program. My dear students, this is a wonderful platform for you to develop and strengthen your skill and succeed your career. So don't sit back as mere listener, rather interact with the experts. Discuss about the topics and learn about the latest information and new skills. I hope this workshop will help you for your future. Once again, welcome you all to this workshop, IWAC-2023. Thank you.
Thank you, sir, for your warm welcome. Next, we are beginning with the inauguration function of the workshop. I would like to welcome Dr. Anil George K., the Vice Principal and Assistant Professor at the Department of Computer Science, St. Thomas College, to deliver the inaugural address.
Thank you. Respected Dr. Tony Thomas, the resource person of the day. Dr. Saju M.I., the Honorable Head of the Department of Mathematics. Dr. Vijay, the convener of the workshop. Dr. Sister Alphonsa Matthew, the Vice Principal. Respected faculty members, esteemed participants, and my dear students. I feel greatly honored to inaugurate the instructional workshop on advanced cryptography organized by the Department of Mathematics of St. Thomas College, Thrissur. This event signifies the college's commitment to academic excellence, innovation, and research rigor in the field of mathematics. First of all, I would like to extend my heartfelt gratitude and congratulations to the Department of Mathematics for taking this initiative to organize this workshop. It is all the more important that the event is being sponsored by DRDO and is being organized in collaboration with association with DRDO and CRSI. Such initiatives definitely provide an invaluable opportunity for the students and the faculty alike to deepen the understanding, expand our horizons, and keep pace with the ever-changing landscape of security. Cryptography, of course, deals with the secure communication. It has been a subject of great interest, great fascination, and importance from the time immemorial. During the times of conflict, during the times of war, during the times of love, whenever confidential and protected information had to be transmitted. But today, cryptography is a very, very big topic, a crucial area in the interconnected world. This workshop that we inaugurate today is a testament to our recognition of this fact. Cryptography, in a sense, is an amalgamation of mathematics and computer science to a greater extent. In that sense, I feel very delighted. I hope this workshop will equip our students, the participants, with the necessary knowledge and skills to tackle the challenges of data security, privacy, and integrity in the digital age. Once again, I would like to extend my heartfelt appreciation to all the participants, the faculty members, especially the faculty of mathematics who have worked tirelessly to make this workshop a reality. I congratulate Dr. Saju and Dr. Viju very specially for the tireless, painstaking efforts. With these brief words, I hereby declare the workshop on advanced cryptography officially inaugurated. Thank you, and I wish you all a fruitful and a rewarding workshop. Thank you.
Thank you, sir. Next, I would like to invite Dr. VGM, the convener of the workshop and assistant professor at the Department of Mathematics, St. Thomas College, to deliver the word of thanks.
Good evening, all. Respected Father Anil George, Tony sir, Saju sir, all other faculty members, participants. I consider it as a great honor and privilege to organize this instructional workshop on advanced cryptography and propose vote of thanks on this memorable occasion. First and foremost, I thank Father Martin Colabrath, Principal of St. Thomas College Autonomous Thrissur. He is a source of constant energy for all of us. Next, I would like to express my gratitude to Father Anil George Concord, Vice Principal of our college, who inaugurated this event. Father Anil motivates us always to conduct such fruitful events, and he always promotes research activities. I would like to thank all our invited speakers, Dr. Tony Thomas, Associate Dean and Associate Professor, Digital University of Kerala, Thiruvananthapuram, Dr. Lakshmi KV, Assistant Professor, TIFAC Core in Cyber Security, Coimbatore, Ms. Lexi Alexander, Scientist, DRDO, Bangalore, Dr. Ajit Kumar Vyasrao, Senior Security Research Engineer, NetApp India Private Limited, Bangalore, Mr. Vishnudas V, former mathematician, Encryption Lab R&D, ITI Limited, Bangalore, Mr. Murthy DHR, Assistant Professor, Department of CSE Presidency, University, Bangalore, and Dr. Saju MI, Assistant Professor and Head of the Department of Mathematics, St. Thomas College Autonomous, Thrissur, for accepting our invitation and for their willingness to share their experience and knowledge in this promising field. Thank you so much for the management of our college for all the support offered in organizing this event. Our financial sponsor, our financial sponsorship is offered from DRDO. I thank DRDO authorities for the support in organizing this workshop. CRSI offered great support to us from the very beginning itself. Thank you, CRSI, especially to Dr. Balasubramaniam and Dr. Binmal Roy for your helping hands. Next, the most inevitable part of this workshop. Dear participants, thank you so much for accepting our invitation and for being here to enrich yourself. Next, I would like to thank all my colleagues for the support. Thank you, Dr. Saju MI, Head of the Department, and all other faculties. Once again, thanking you all. Let us start our sessions. Thank you.
Thank you, ma'am. I now request Dr. Shaju MI to introduce the resource person for the session.
Okay, today's first section handled by Dr. Tony Thomas on the topic, the quantum threat to cryptography. Dr. Tony Thomas is an Associate Dean, Associate Professor at the Kerala University of Digital Sciences, Innovation and Technology. He is also visiting professor of ISR Thiruvananthapuram. His current research interest includes biometrics, multimedia security, and cryptography. Dr. Tony Thomas completed his post-graduation with the first rank from IIT Kanpur. He has also completed his PhD from IIT Kanpur in the same area, cryptography. He has 5 books and nearby 70 scientific publications to his credit. He had served as a research associate in the R&D lab Bangalore and a research fellow in the School of Computer Engineering Singapore during the period 2008 and 11. On behalf of all, once again, I welcome Dr. Tony Thomas sir to the event. Over to Tony sir. Thank you.
Thank you, Dr. Saju, for your kind introduction, and good evening to all. So first of all, I thank all the organizers for giving me an opportunity to talk something on cryptography and the challenges ahead. So let me open my presentation. Okay, I hope you can see my slide, right?
Okay, sir. Okay.
Yeah. So today's topic is quantum threat to cryptography. So I will be talking about the threat which is occurring to or which may happen to our cryptographic systems due to some advancements in quantum world. Okay, so I am part of the Kerala University of Digital Sciences, Innovation and Technology, which is also known as Digital University Kerala. We have a beautiful campus in Thiruvananthapuram. It's a state university where we run masters and PhD programs in various areas related to digital sciences. So I am part of the computer science and engineering school here. We have MSc in cybersecurity, MTech in cybersecurity, and PhD in cybersecurity. So BSc students, BSc mathematics students, or BSc science with mathematics as a subject, BTech, they come for our MSc cybersecurity program. We have MTech cybersecurity engineering, where BTech as well as MSc students can join, and we also have PhD program. So that is roughly about our university and the academic programs here. Currently, we have only postgraduate programs. We don't run any undergraduate programs. So let me start from the basics cryptography. I hope almost all present here may be familiar with the basics of cryptography. So I will start from the very basics. I will not go into the details of each and everything, but I will start from the classical or ancient crypto systems to the current trend in cryptography. So cryptography is a system that provides techniques for mangling. So as one of the father was talking, right? So cryptography is we have to protect the messages or convert the messages into unintelligible form so that secure communication is possible. So there is a sender and the receiver. So there are two parties. They want to exchange messages so that confidentiality of the message is kept. So the normal message is usually called a plain text. We convert it into something into an unintelligible form, which is called a ciphertext by an algorithm called the encryption algorithm. Then this resulting thing is called a ciphertext, which is transmitted through any channel, which is usually called as unsecured channel. Unsecured channel is a channel with no kind of protection. So if you send a mail, or if you send a message, or if you make a phone call, all these are unprotected or unsecured channel, right? So at the receiver side, receiver has a key and a decryption algorithm. So receiver puts the ciphertext into the decryption algorithm along with the key, and he can obtain the original message, right? So a crypto system consists of these are the main ingredient. There is an encryption algorithm, decryption algorithm, keys, right? And we all know that security of a crypto system depends upon secrecy of the key. Right? It is not about the secrecy of the algorithms. Now we have two different settings. One is the symmetric key setting and the other is the asymmetric key setting. In symmetric key setting, the encryption key used for encrypting the message and key used for decrypting the message are same, or one can be easily computed from the other. If you know the encryption key, you can easily compute the decryption key and vice versa. The other context is the public key cryptography, where you have different keys, one key for encryption and a different key for decryption, and they are asymmetric in nature. That means if you know one key, you cannot easily get the other key, right? So one key doesn't actually help you to, knowing one key doesn't really actually help you to get the other key. Okay, so we all started learning cryptography with the classical crypto systems. Cryptography is an old subject, thousands of years old. People used very simple kind of cryptographic mechanisms or encryption mechanisms. So one of the oldest cipher we all know is the Caesar cipher, in which a character is replaced by the encryption process is a character is replaced or substituted by another character. For example, a character at 3 places away. So if A is the character occurring in the plain text, I will replace the ciphertext, I will replace A with D. Similarly, if B is occurring, I will replace B with E. Right. In order to decrypt, wherever E is occurring, I will replace by B. Right. So this number, so each character is shifted by 3 places. So this 3 is the key. 3 is the key for encryption. Similarly, 3 is the key for decryption. And another, so this actually is what is called a substitution cipher. A substitution cipher is a cipher in which you substitute a character by another character. For example, in this case, A is substituted by D or C is substituted by F, right? So the classical crypto systems, if you look at, they are based upon basically two operations. One is substitution, the other is permutation. So in substitution, you substitute a character occurring in the plain text with another character. It can be from the same alphabet or it can be from a different alphabet. For example, A can be substituted with a C, or A can be substituted with a, say, alpha from a different alphabet. Right. The another thing is, if you look at, this is the second figure, if you look at, there is another classical crypto system in which, so there is a cylindrical rod kind of thing in which a strip is there, right? So you write the message, you wind this strip along this cylindrical rod, then write the message on the top of it in the horizontal direction. You can see send more troops to southern, etc. Right. So then you take out, when you take out the strip, you can see that the characters occurring in the strip are a rearrangement of what you wrote, right? So in the strip, you will find that actual message S is followed by E followed by N. But when you take out the strip, in the strip, you will find the characters are occurring in a different order. S is followed by T, T followed by S, and so on. Right. So there is a permutation occurring there. Right. So this is an encryption mechanism in which ciphertext is generated by rearranging the position of the characters occurring in the plain text. Right. So at the receiver side, the receiver also has an identical cylinder, a cylinder with exactly the same radius. So the receiver also will wind this strip on the same kind of cylinder. Then he can read the message in the horizontal direction, right? So in this case, the key is the radius of the cylinder, right? If you change the radius, you will get a different key, right? So these two concepts, one is the substitution concept and permutation concept. This concept originated thousands of years back, and surprisingly, these two things are two major components in any modern crypto system you use. If you take any modern crypto systems, you will find that the substitution operation and permutation operations are two most important operations. Modern crypto systems are not as simple as this. They have many operations. Along with the many operations, you will find that the substitution and permutations are two core operations occurring there. Now, people were happy in olden days with all these kind of simple crypto systems. And during the World War time, we people used mechanical machines, rotor machines for doing cryptography, right? So these are some these figures actually. These figures you can see some of the old cryptographic machines, right? So they will type. It contains a different kind of cylinders. If you vary the arrangement of the cylinders or arrangement of these rollers, you will get a different ciphertext. So these are mechanical kind of crypto systems which people used around 1940s, 1930s, 1940s, etc., especially during the World War. Now, after 1950s, we saw major evolution in computer systems, right? From 1960 onwards, we see tremendous progress in the computing power. We saw mainframe computers coming, mini computers, micro workstations, then personal computers, right? So when we were all in schools or in our colleges, laptops were not there. Right? We were using only, even personal computers were also rare. Now almost everybody has a laptop, everybody has a smartphone, right? So smartphones are so capable that they can do most of the things which a workstation or a laptop can do, right? So we see a lot of tremendous progress in the computing domain. Computers are becoming more powerful and more capable. So what is their effect on the conventional crypto systems? So we saw the Caesar cipher system and other classical cipher systems, right? All these are very or very simple crypto systems. All these systems, see, if you look at Caesar cipher, by just analyzing the pattern of characters occurring in the ciphertext, or if you look at any classical crypto systems, a simple program written for a normal computer can easily break that crypto system, right? Because the number of possibilities are too small, number of keys are too small, the size of the key is too small, right? So a modern computer can easily break these classical crypto systems with their computing power, right? So all these classical crypto systems became obsolete by around 1950s, 1960s, right? So we just study them for their historical importance and uh, their significance, right? But they don't have any academic, any commercial value, or even not much academic value. Now, with this evolution of computing technology, and so we saw that computers every day, better technologies are coming, right? Computers are becoming, or chips are becoming smaller in size. Their computers are becoming more and more powerful, right? So we need much more better crypto systems. Crypto systems like Caesar cipher or Railgun cipher or other things, rotor machines, these cannot provide security because they can be easily broken. The number of possibilities, the number of trials one can do are too limited, are too less in number, right? So one can even try all possible keys. A modification of the Caesar cipher is the shift cipher. In Caesar cipher, we are shifting by an amount 3. Each character is replaced by another character 3 places away. So we have another version called a shift cipher, in which each character is shifted by 4 places or 5 places or 10 places. Maximum 25 possibilities are there, right? So if you encrypt any message with a shift cipher, you can easily decrypt by trying all possible 25 keys. Right, so number of keys is very limited. So even exhaustive search or brute force attack, with brute force attacks or exhaustive search, we can easily break crypto systems. So what we want is more complex crypto systems with a big, which actually deals with big numbers, not small numbers. The number of possible keys should not be just 100 or 1000, it should be millions or billions, right? So the modern cryptography actually born with two major appearance of two major cryptographic mechanisms. One is the DES, data encryption standard in 1970s, and the other is public key crypto systems proposed by Diffie and Hellman, right? So this appeared around 1970s. So this NIST, National Institute of Standards and Technology in US, so they wanted actually a encryption mechanism, symmetric key encryption mechanism for commercial use, for encrypting commercial data or for day-to-day communication. So they, along with the support of IBM, came up with this data encryption standard algorithm. This DES is, or data encryption standard, is what we call as a block cipher. A block cipher. So if you have a data, it encrypts 64. Whatever message you have, it converts it into bits, zeros and ones. Then it will encrypt 64 bits of data at a time using a key of size 56 bits, right? So in 1970s, this was a very good algorithm because this data encryption standard, or it is a symmetric key algorithm. It uses many operations like the substitution operation, shift operations, shifting bits to the left, or substituting the bits, or adding the keys, doing this many rounds, many times, right? And the key size is, most important thing is, the key used for encrypting and decrypting in DS algorithm is 56 bits. That means the number of possible keys, right? So it is a string of zeros and ones of length 56, right? So in the first position, 1 or 0 can occur. Second position also 1 or 0 can occur. Similarly, at the 56th position also 1 or 0 can occur, right? So the total number of possibilities for such keys is 2 to the power 56, right? 56 positions are there. In each of these positions, you can put either 0 or 1, right? So total number of keys of length 56 bits is 2 to the power 56, which was a very big number at that time, right? So this DS was considered to be a very good cipher. It was a very good cipher, a cryptographic mechanism, and it survived for around 20-25 years till the beginning of 2000, right? So as I said earlier, computers and computing power increases day by day, right? So whatever crypto systems you have today, they are secure for today. Tomorrow or day after tomorrow, or even after 10 years, we cannot say that they are going to be still secure, because almost all these cryptographic mechanisms depends upon, their security depends upon our available computing power and resources. If you have better computers, better computing mechanisms, many of the encryption mechanisms we may be able to break, right? So since we don't have that much computing capabilities right now, they are secure, right? So this is the thing about symmetric key cryptography. At almost the same time, a major breakthrough came, which is the introduction of public key cryptography by this Diffie and Hellman. So they proposed the concept of public key cryptography as well as key exchange problem. What is key exchange problem? See, if I am using a symmetric key crypto system, suppose Alice and Bob want to exchange a message in a symmetric key cryptographic setting. They have to share a key. Alice or Bob should use the same key for encryption and decryption. So they have to share the key. If Alice is at a place X and Bob is at a different place Y, it is practically difficult to share the key securely. You cannot send your key through email. You cannot send your key through WhatsApp message, or you cannot send your message through a phone call. They are all insecure channels. Remember, security depends upon secrecy of the key. So key has to be very securely exchanged. Either there should be a mechanism to securely exchange the key, or they have to meet in person. If somebody is in, say, in the other part of the world like USA and somebody is in India, it is physically extremely difficult for them to meet and exchange the key. So this is the key sharing problem. So symmetric key cryptography is a very good mechanism, and most of the security mechanisms or where confidentiality is provided by symmetric key encryption mechanisms. But the challenge there is how to exchange a common, or how to share or establish a common key between sender and receiver, or between the two parties. So this Diffie and Hellman came up with a very beautiful mechanism. They came up with a very beautiful mathematical mechanism called Diffie-Hellman key exchange protocol. It uses a very beautiful idea or concept in mathematics, which is called the discrete logarithm problem. Right. So by making use
ChatGPT
of
is the
a
biggest growth hack to
problem called the discrete
100x your
logarithm problem,
productivity, no matter who you are.
they came up with an idea in which these two parties, Alice and Bob, will exchange numbers. Alice will send numbers to Bob. Bob will send some numbers to Alice. At the end of this transaction, Alice and Bob will be able to compute a common key from whatever they have and whatever they received from the other party. But whoever listening to their communication channel, this communication channel between Alice and Bob is an insecure channel. They will not be able to compute the key, because that is actually the core concept of Diffie-Hellman key exchange protocol. And it actually, in order to break this security, an attacker has to solve this problem called a Diffie-Hellman, or they have to solve this problem called a discrete logarithm problem. Logarithm in a group. So that is why it is called a logarithm, discrete logarithm. They have to find the logarithm of something in a group, which is not a very easy thing, right? And in that, they published a research paper in that they said that it is possible to have a crypto system in which there are two keys. One key is used for encryption and a different key for decryption. Until then, the cryptography meant or considered to be only symmetric crypto system. That is actually the natural way one can think and do, right? You have one key to encrypt, you have to use the same key to decrypt or get the message back, right? So it is weird. It's not straightforward to think that you have one key to encrypt and a totally different key or totally different number you will use to get the message back. And Diffie-Hellman said that it is possible to do that. Unfortunately, they could not come up with a way of doing it. It was 2 years later that three people, Rivers, Shamir, and Adelman, came up with the first public key crypto system, which is called the RSA crypto system. This RSA crypto system is a public key crypto system. The advantage of a public key crypto system is that there is no need to secretly share the key. Each person will have a pair of key, which is called the public key as well as the private key. This one key is public key, which is the encryption key. You can publish it, you can send to anybody. So the public key of all are known. So if I want to send a message to Alice, I will just pick up the public key of Alice and encrypt the message using the public key of Alice and send to Alice. Alice you can only decrypt using her decryption key, which is called the private key, right? So if I want to send a message secretly or confidential message to say Bob, I will pick up the public key of Bob, encrypt the message using the public key of Bob, send to Bob. Only Bob can decrypt and get the message because only Bob knows the decryption key or the secret key. So the security, why this? So they propose a crypto system called RSA, or RSA corresponds to reverse Shamir and Adelman, and an attacker can see something happening, but he will not be able to decrypt the message, or he will not be able to get the decryption key. There also actually the security, we have to prove that the system is secure. So the proof is based upon the fact that there is a mathematical proof that RSA crypto system is secure. Because if somebody wants to break RSA crypto system, he has to factorize large numbers, which is called the integer factorization problem. So if I give you a very large number, and if I ask you to find its factors, you may not be able to do in your lifetime. So if the number is a very big number, there are no easy way to factorize large numbers. But we can easily multiply numbers and get their product. But there are no easy way to find factors of large numbers, especially if I choose two large prime numbers. Suppose I have a prime number P, another prime number Q. If I multiply them and get the product, and I give you that number, and I ask you to give me the factors P and Q, if this number is a big number, whatever computing power you have, you use all the computing power available on the earth today, you may not be able to get the factors in your lifetime, right? Because there are no easy way to, there are no easy what we call algorithms to factorize numbers. We can easily multiply and get their product. We can easily find GCD of the numbers. We can use the Euclidean algorithm to find the GCD of the numbers, but there are no easy algorithms or easy ways to factorize numbers. So the RSA crypto system, the security depends upon what is similarly, but the DES algorithm, when the computing power increased, DES became, it was more easy to break DES. So by the end of 1990s or before 2000, it became evident that DES symmetric algorithm is not going to survive. So they sought for a replacement, and a replacement called the AES, Advanced Encryption Standard, appeared. Okay, so if you look at the Diffie-Hellman key exchange, you can see the mathematics happening here. So you have this number FP star or ZP star, where P is a prime number. FP star stands for all the numbers from 1, 2, 3, etc. P minus 1 with the operation multiplication modulo P. Right. So the Diffie-Hellman exchange protocol depends upon this simple, beautiful mathematics. So Alice will, so there is a G. G is You can say it is a generator of FP star. FP star or ZP star is a group or a multiplicative group. That is a group with multiplication operation. What is the operation? Multiplication modulo P. And it is also a cyclic group. Cyclic group means any element can be in the group can be generated from one element. So there is an element G square, G cube. If you take G square modulo P, G cube modulo P, G to the power 4 modulo P, you will get all the elements in the group. If P is equal to 7, F7 star, which is Z7 star, consists of the elements 1, 2, 3, 4, 5, 6. The operation here is multiplication modulo 7. So if I multiply two numbers 4 and 4, 4 into 4 is 8. 8 modulo 7. That is, I multiply 4 and 4. So I will get 16. Sorry, not 8, 16. 16 modulo 7. So I will divide 16 by 7 and get the remainder. So the remainder is 2. Right. So 4 into 4 is equal to 2 here. Right. So in this Diffie-Hellman exchange, you can see what. So Alice and Bob want to establish a common key. So Alice will choose a random number, say A, and compute G power A modulo P. G is a generator. G power A is G into G into G A times modulo P. Similarly, Bob will compute G power B modulo P. Then Alice will send A, G power A to Bob. Bob will send B to Alice, that is G power B. Now, after this, Alice can compute. Alice got B, which is G power B from Bob. Similarly, Bob got A from Alice. So Bob will compute A power B. But what is B power A? B is equal to G power B, which is equal to, now B power A is going to be G power B whole power A, which is G power AB. And Bob got A from Alice. A is G power A. So he computes G power AB, which is also G power AB. So the common key is G power AB. So if you look at this G power AB is the common key. What is capital A? Capital A is G power A. This small a is called the discrete logarithm of capital A. If P is a very large prime number, it is extremely difficult to get this number A. There are no easy way to get A. It is a computationally very difficult, hard mathematical problem. If P is a large prime number means how large? P will contain some hundreds of digits. It is not a small number. P will be a prime number with hundreds or 200 or 300 digits. Now, G is a generator and you compute G power A is equal to capital A. And if you give A to somebody and ask, tell me what is the A? What is the A so that G power A is equal to capital A? The best computer also or computing resources also, nobody can get this answer. Right? This is called the discrete logarithm. Finding this A, given A, capital A, finding the small a, the power. This is similar to the normal logarithm, but here the setting is a finite group, that is why it is called a discrete logarithm. Right. So Alice is sending G power A to Bob. Bob is sending G power B. Right. An attacker, or we call it as eavesdropper, somebody listening to what Alice is sending to Bob, what Bob is sending to Alice. Right. They will see G power A going, G power B going. They will see capital A, which is G power A, capital B, G power B. Right. Whatever magic they do, they will not be able to get G power AB. Alice and Bob can calculate G power AB. Alice can compute G power AB. Bob can compute G power AB. But whoever listening to Alice and Bob, They will say G power A, G power B. There is no easy way to get G power AB from G power A and G power B. If you multiply G power A and G power B, you will get G power A plus B only. Fine. So that is why this is called the Diffie-Hellman key exchange mechanism. And you can see that this mechanism is secure provided the discrete logarithm problem is difficult to solve. That means the moment you see Diffie-Hellman the discrete logarithm problem is easy to solve, the Diffie-Hellman key exchange becomes insecure.
Sir, one doubt, sir.
Uh,
Sir, you said a trusted party chooses and publishes a large prime number, no, in that presentation. Who's
where
this trusted party? Is it Alice or Bob or some third party?
this prime number P is selected by Alice and Bob.
Okay.
In this protocol, this P is selected by Alice and Bob together, and this G is also, the generator is also selected. Or Alice can select or Bob can select and tell the other party.
Okay, sir.
Eh?
So how do they exchange? They have to meet in person or like
They
how?
don't have to, this P, there is no secrecy about P, there is no
Okay.
secrecy about G, there is no secrecy about uh, ZP or FP. The secrecy is about the small number A. This is a secret of Alice, this is a secret of Bob.
Okay.
Alice will not tell the small a to anybody. Bob will not tell the small b to anybody. As long as that they are kept a secret, this mechanism is secure.
Okay, and even Alice and Bob don't like Bob doesn't have to know A and Alice doesn't have to know B also. They just have to know G power A.
Yeah, G power A, right. So an attacker will know G power A. Attacker will know G power B, but he cannot get A or B from G power A and G power B because he has to solve the discrete logarithm problem. Right.
Okay, sir. Thank you.
Yeah. And there are no easy or algorithms, mechanisms to get the discrete logarithm. So if you work with large numbers, you will see that you may not find any pattern between capital A and small a, right? Because it repeats after some time. It repeats. Okay, so let me go a little more faster.
This repetition, sir, is because of that modulo part.
Because of the modular part.
Okay, sir.
So the modern cryptography, I said, roughly started with the emergence of DES symmetric algorithm, similarly RSA and Diffie-Hellman asymmetric algorithm. So after that, many newer algorithms appeared. Some remained as secure, some became insecure. It is easy to construct cryptographic algorithms, but it is extremely difficult to construct secure crypto systems. Many crypto systems appeared and they survived for 1 or 2 years, or some survived for just few months, and they all collapsed because of many security weaknesses. So ciphers, we have classical ciphers. We started with the classical ciphers and modern ciphers. Classical ciphers, basically two categories are there: substitution ciphers, transposition ciphers. Then we have monoalphabetical ciphers, polyalphabetical cipher. Monoalphabetical cipher means every time when you encrypt one character, suppose A is changing to C, every time A will be changing to C only. But in polyalphabetic, first time A may be changing to C, second time A may be changing to some F. That is called polyalphabetic cipher. Then transpositional ciphers, some may use key, some keyed ciphers, keyless ciphers. Then we have the Caesar cipher, which is to explain, is a monoalphabetic cipher. Then polyalphabetic cipher, it's a Wigner cipher. Okay, then that is all about classical ciphers. Modern ciphers, we have symmetric key and asymmetric key cipher. Symmetric key is divided into block ciphers and stream ciphers. Block cipher means it encrypts a block of data, a block of bits, say 128 bits at a time. Stream cipher encrypts 1 bit or 1 byte at a time. The main difference is that block cipher, there is a key. The entire message is divided into pieces called blocks, and each block is encrypted using the same key. all the time. But in stream ciphers, data is coming as a stream, zeros and ones, continuous stream. There will be a continuous stream of keys also. Key also will be coming as a stream. So this stream of data and stream of keys will be mixed up using XOR operation. That is the idea of stream cipher, right? So the main difference between block cipher and stream cipher is in block cipher there is one key and the message is divided into different pieces of same length or blocks. Each block is encrypted with same key. In stream cipher, data is coming as continuous stream, zeros and ones, 0, 1, 1, 1, 1. So data is flowing. There will be a flow key also, key stream also will be there. So the corresponding data and the key will be mixed up. Mixing is just XOR operation. So in that way, so stream ciphers are very fast in nature. Block ciphers are a bit slow. So suppose if you want to encrypt files or hard disk data and keep it somewhere, you use block ciphers. Suppose you want to encrypt your file in your system, you use a block cipher. But if you want to send messages to somebody, somebody is at the receiving end, it is a continuous process, it's a streaming process. Data is flowing. Then you encrypt the message using stream cipher. At the receiver side, he or she will decrypt continuously. So data encryption and decryption process happens continuously. We have many block ciphers like AES and DS are the most prominent one. Then triple DES, IDEA, Blowfish. Then many stream ciphers, ISAC, Quadfish, RC4, Seal, etc. RC4 is one of the widely used and very popular stream cipher. So we use similarly asymmetric cipher. We have RSA asymmetric cipher. DSA is a digital signature algorithm. Diffie-Hellman is a key exchange protocol. Okay, so if you open the internet, you will see the application. The moment you do an online banking, or if you enter into a website which starts with HTTPS instead of HTTP. So all the communication from this client, from the browser in your machine to the server. Suppose I am doing online banking with the, say, SBI. So I open a browser, right? So browser in my machine will communicate with the SBI server located somewhere. This communication is going to be a secure communication. The account numbers, the password, other information you send, all will go in encrypted fashion. And we use these kind of public key cryptography, digital signature, and secure key exchange mechanisms for the secure transaction. Right. So the RSI crypto system and other crypto systems like elliptic curve and the key exchange mechanisms like the Diffie-Hellman, all these are actually used. We are not, or common people are not knowing actually what is happening, but every day the moment we are using any secure thing or even just using an HTTPS, accessing an HTTPS URL, most of the sensitive data will be flowing in encrypted fashion only. So the public key, so we have seen public key cryptography and classical cryptography. Public key cryptography it is very nice because you don't have to share the key. But public key cryptographic algorithms are mathematically very complex algorithms. Symmetric algorithms like DES, AES are mathematically simple algorithms. They use permutation, substitution, some rotations, shift operation, etc. Mathematically, they are very simple operations. Whereas if you look at many asymmetric key or public key cryptographic algorithms, they use exponentiations in some group or do some operations in what is called an elliptic curve group, or some operations in what is called a lattice, integer lattice, etc. These are all mathematically highly intensive operations. So that means public key algorithms are not what we call not efficient. They require a lot of time. If a symmetric key encryption can be performed in 1 second, same encryption if you use an asymmetric algorithm, it may take 1000 seconds. That much difference will be there. So usually the asymmetric key cryptographic algorithms are used only for sharing keys. You can use Diffie-Hellman exchange to share key. Another way to share key is, suppose I want to share a key with Alice. I will choose some random key and encrypt the key using the public key of Alice and send to Alice. Then Alice will decrypt and Alice will get the key. Suppose my key is 1234. Right. I want to send this 123, exchange is 1234 with Alice. Right. I will make use of the public key encryption algorithm. I will encrypt 1234 with the public key of Alice. Send to Alice. Alice will decrypt and get 1234. After that, we will communicate with the key 1234 using symmetric key algorithm. So all the public key algorithms, encryption mechanisms are used basically to encrypt keys, not to encrypt large files. Once you encrypt the key and share the key, all further encryption mechanisms will be performed using symmetric key algorithm. Another important application of public key algorithm is the digital analog of our signatures, which is called the digital signature. So basically, public key algorithms, public key cryptographic or asymmetric key cryptographic algorithms are used for establishing keys between two parties and for digitally signing. In the example I said, I am opening the website of SBI Bank, right? So this my browser in my machine, my system is opening the website. Now whatever I am typing here is going to the server of SBI, right? It has to be encrypted. My account number should be encrypted. The password should be encrypted. The amount I enter or other instructions I give, all should be all are confidential. Right. So first, the browser, my browser, I may be using a Firefox. This browser will establish a key with the server, SBA server. Right. So what the browser does is, the browser in your machine will ask for what is called the digital public key certificate of SBA. So the SBA server will send the public key certificate to my browser. This public key certificate will contain the public key of that SBA server, right? So I can get the public key of the SBA server. Then the browser will, as I said just now, use this public key to establish a common key. So for example, my browser may generate a key. This key will be encrypted with the public key of the SBA server and sent to it. Server will decrypt it. So thereafter, the communication between my browser and the server somewhere will be encrypted using that key. Right. Okay, so there is something called the SSL protocol, secure socket layer protocol. This mechanism is actually called the SSL protocol or secure socket layer protocol, which is actually there in many web applications, especially if you look at HTTP, any website whose address is starting with HTTPS, then it is a secure, transactions will be secure. Okay, if it is just HTTP, then the security mechanism may not be there, but HTTPS, if it is starting with HTTPS, then definitely this security mechanism is there. Data will be exchanged in confidential way only. So this mechanism is called the SSL or secure socket layer protocol mechanism. Okay, so I said factorization is a very difficult problem and very interesting problem. Many people have tried to factorize large numbers, no success. Till now, we don't have any efficient way to factorize large numbers. So you can see here, see 680, if I try to factorize 23, 4, Then 20 can be factorized as 4 into 5. 34 can be written as 17 into 2, etc. So the prime factorization of 680 is 2 cube into 5 raised to 1 into 7 raised to 1. Right. This is 680 is a small number, three digit number. Right. If usually the numbers we express as number of bits, we convert the number into binary form and count how many bits are there. For example, if the number has 512 bits, MIPS, number of instruction, millions of instructions per second. See, you can see that when the size here, when the size is just 512, the number of years take to break such a number or to factorize such a number is 3 into 10 to the power 4. But when the size becomes say 4 times of that, say 2048, you can see the size, the number of years required to factorize such that kind of a number is 3 into 10 to the power of 20. You cannot imagine, right? So the time required to factorize large numbers can go beyond even the age of the universe.
So
Not
what is
because
MIPS, sir? MIPS?
millions of instructions per second.
Okay.
Just search. Okay, so it is not that it is impossible to factorize large numbers. The only thing is we don't know how to factorize. We don't know at present. Tomorrow, somebody or you can come up with a nice way of factorizing large numbers. Then all these numbers will go down. The only thing is that we don't have that knowledge. We don't know whether there exists an easy way to factorize large numbers. Sometimes it may be impossible. That also we don't know whether it is impossible to have an easy way to factorize large numbers. Sometimes, so far nobody has come up. Tomorrow or maybe after some couple of years, somebody can come up with a better way of factorizing large numbers. Okay, so similarly, the discrete logarithm problem, which I mentioned, see, all this depends upon powers. If you look at, say, modulo 19, suppose a is equal to 1, if you take any power of a is 1, 1, 1, 1. If a is equal to 2, the powers are 2, 2 raised to 4, 2 raised to 8, 2 raised to 16, etc. Modulo 19. 2 raised to 2, 2 square is 4, 8, 16. Then 2 raised to 5 is 13, right? 2 raised to 6 is 7, 2 raised to 7 is 14, etc. Right? So if I, for example, if I look at 18 here, 18 here, the discrete log of 18 is 9. Similarly, the discrete log of 3 is going to be 13, right? So finding this number, there is no easy way to find this number. I will give you just 3 and I will tell that it is modulo 19. You have to tell me what is this power. It is 2 power something is 3, right? This something is not easy to find. Just like the factorization problem, this is an extremely difficult problem. And security of most of the modern crypto systems based upon these two problems. That is, factorizing large numbers is difficult, finding discrete logarithm is difficult, right? That means these crypto systems are not secure, may not be secure forever. Just like I mentioned now, somebody can come up with an easy way to factorize or find discrete logarithms, or somebody can come up with a better way, better computing system to factorize large numbers or to find discrete logarithms or to do the operations in very faster mechanism. Just like we saw the evolution of computers, right? Starting from mainframe onwards. Now we have mobile phones capable of doing the normal kind of operations, right? Now we are entering into something called a quantum evolution. We have computers based upon the principles of quantum mechanics, right? This is going to be a revolution in computing technology or computing systems. Quantum computers are computers based on principles of quantum mechanics or physics. They have exponentially high capabilities. Exponentially high capabilities means if my computer can store 3 bits of information, 3 bits, quantum computer may be able to store 2 power 3, which is 8. Right, that is the exponentiation. Right, that much it can store information. It can store. Similarly, it will be exponentially faster. That means if an ordinary computer takes 8 seconds, my quantum computer is going to take 2 seconds. That means many of these problems can be solved easily using quantum computers. If we can solve these problems easily, that means many of the existing crypto systems can be broken. Right. This is actually what I meant by quantum threat to cryptography. Right. Until few years back, cryptography was basically a fascinating subject of mathematicians. Right. Now the field is changing. It is not the monopoly of mathematicians. It is now a branch of mathematics, physics, and computer science. Right. So many of the modern or emerging security systems are going to be quantum computer or quantum computing based. So I said that we have efficient algorithms. Some things we can easily solve. That is, we have efficient algorithms. For some problems we don't have efficient algorithms. Multiplying numbers efficiently we can do. Finding GCD of two numbers, that is efficiently you can do. Factorizing number, no efficient way. So this is usually expressed in terms of the complexity, constant complexity, logarithm of n complexity, n complexity, n log n complexity, n square, 2 raised to n exponential complexity, and factorial complexity. Right. So this actually says the complexity. If the complexity is log n, it is okay. Complexity is n, it is okay. If complexity is 2 power n, we say it's exponential complexity. That means it will take exponential time. If something is taking 60 seconds, this is going to take 2 power 60 seconds. Right. So many of our problems like factorization, discrete logarithm are near to exponential complexity. So, okay. So let me, before entering this quantum discussion about quantum setting, so we have a puzzle. So we have 2 rooms. Right. One room has 3 light switches, and one room has these switches. The second room has these lights. Right. But you don't know which bulbs are connected to which switches. Right. For example, first switch may be connected to the second bulb, second switch may be connected to the third bulb, third switch may be connected to the first bulb. Right. You don't know. Okay. So switches are in one room and bulbs are in other room. If you are in one room, you cannot see what is happening in the other room. Now the challenge before you is you are supposed to enter a room only once. And you have to identify which switch corresponds to which bulb. All bulbs are functional. If you switch on a bulb, you can see the corresponding bulb lighting, right? Now this puzzle, this thing, whether you can solve this puzzle. So there are 2 rooms. One room contains the switches, the other room contains the lights. If you are in one room, you cannot see what is happening in the other room. Now the challenge before you is you have to identify. You are supposed to enter each room only once. You have to identify which switch corresponds to which bulb. Right. How do you figure out which bulb is connected to which switch? We are all mathematics people, right? With mathematics, we cannot solve this problem. Right? Whatever mathematical technique you apply, you cannot solve this problem. There is no configuration for switch. You can switch on first switch. If you switch on first switch, the corresponding bulb will light up, but you don't know which second and third bulb corresponds to which switches, you cannot say. So you switch on 2 switches, then also the confusion will be there. If you switch on 3 switches, all the lights will be on, but you will not be able to identify which switch corresponds to which bulb, right? So whatever combinations and possibilities you try mathematically, you cannot solve this problem. So mathematically, you cannot solve this problem, but if you rely on physics, you can solve this problem. So how do you solve this problem? As a physics problem, there is a solution. In the switch room, you turn on 2 switches, right, for a few minutes, and then turn one off, right? For example, the first switch and the second switch I am switching on, right? So 2 bulbs will be on here, right? Then I switch off one of them. For example, I am then switching off the second switch. I off the second switch. Then I enter into the bulb room. Then I will see one bulb lighting. Then I know that this bulb corresponds to that switch. So I can identify which switch corresponds to that bulb. Then the next is the important thing. I will touch the other remaining 2 bulbs. Among the other 2 remaining bulbs, one switch bulb will be hot and the other one will be cold, because the bulb which was switched on earlier will be hot. So I will be able to identify the switch corresponding to that bulb, and the remaining bulb is corresponds to the remaining third switch, right? So by making use of this physics principle, you can solve this puzzle, right? So always mathematics may not be enough to solve some problems. So in that case, we rely on physics. Okay, so information is actually physical, right? It is not something abstract, right? Information we always represented as in the physical form. For example, the conventional computing systems, information is represented as bits, zeros and ones. If switch is on, it is 1. If light is on, 1. If light is off, it is 0. If switch is on, it is 1. If switch is off, it is 0. If head is up, it is 1. If tail is up, it is 0. In that way, right? So the information we represent in the physical form. Now, the Feynman in 1982, he said that there may be quantum systems that cannot be simulated efficiently on a classical computer, right? So the computers are used to simulate whatever things happening around us, right? You can simulate, you can predict whether there will be rain tomorrow, or whether there will be an outbreak of COVID, or there will be a class tomorrow, or you can forecast many things you can, whatever happening around. But can we use one classical or normal computers to model or understand or predict the things happening inside the quantum world, the world of atoms, or inside that the quantum level? Feynman said that there may be quantum systems that we cannot actually, with normal computers, we cannot actually model what is happening inside the quantum world. So he said that, so we have basically two laws of physics. The classical physics we know, which is mostly the Newtonian physics, and the physics happening inside the quantum, the small world. These two physics are different, right? So the classical computers are based upon classical physics ideas. Why can't we make, if a classical computer cannot model or capture what is happening in the quantum world, why can't we make a computer using these principles of quantum mechanics? So the Feynman proposed the idea of creating machines based on the laws of quantum mechanics. So quantum physics deals with the small particles, like electrons, protons, neutrons, their interactions. These are called elementary particles. So their properties and behaviors are very strange from what we see in the normal or classical world. For example, a quantum particle can go through two places at the same time and can interact. Quantum physics is full of counterintuitive or mysterious and lot of paradoxes. So attempts started. People tried to make computers based upon quantum principles. This Deutsch 1985 proposed machines using quantum process might be able to perform computations that classical computers. For example, I said that we cannot factorize large numbers easily with our normal computers. Right? Probably quantum computers can do that. Or quantum computers can find discrete logarithms of problems easily. So this David Deutsch developed a quantum Turing machine showing that quantum circuits are universal. That means they can be used to solve any problem. So there are many properties of classical information and quantum information. Classical information is information represented using classical physics. Quantum is using quantum physics. For example, classical information, zeros and ones, I may be represented using if a light is on or light is off. But quantum information I may be depending upon photons or electrons to represent the information. See, in the puzzle I explained, information is bulb on or bulb off. So information is represented by on or off of the bulb. That is a classical situation. When I want to represent information, see, computing means you have to represent information. Computer is nothing but information is there. This information is put somewhere, and these things are manipulated, and you will get results. Right? Lights on, light off, many combinations things will happen. Finally, some lights will be on, some lights will be off. That is the output. Similarly, so information is represented on classical things, physical things, and physical things are processed, and you will get the results. Similarly, if you represent information on quantum things like photons or electrons, and if you process these photons or electrons, you can process the information and get outputs. For example, if you do this problem of factorizing large numbers, if you somehow put it on the top of photons or electrons and process them, you may be able to get the factorization of the numbers, and that is possible. Actually, that is what we will see. So main properties of classical information is that it is easy to store, transmit, process classical information in time and space. If I have an image, for example, I can do whatever I want with that image. I can copy it, I can cut it, I can make any copies, any digital copies I can send. It's easy to make copies of classical information. And if I take an image, I look at the image, nothing is going to happen to the image. I am not disturbing this. But in the quantum world, the story is entirely different. It is difficult to store, first of all, transmit and process. There is no way. You cannot copy a quantum information. I can make infinite number of copies of my digital image, but we cannot copy a quantum information. The measurement in quantum information destroys it. I can measure anything, I can read any value in my classical setting, but in the quantum world, the moment I try to measure it, it gets disturbed. So a lot of these are actually the fundamental difference between classical world and quantum world. In a classical, but the advantage here is that in classical world, a register can store exactly if my memory has n positions. In each position, I can store 0 or 1, second position 0 or 1, 0 or 1, right? So it will store an n-bit string. But if this is a quantum register is each element in the quantum register may be a photon or maybe a quantum particle. Then each register, each element is not just storing 0 or 1. It can store both 0 and 1, which we call actually superposition of zeros and ones. So the first bit, which we call it as quantum bit or qubit, the first position you will see that both 0 and 1 you can put there as a superposition, as both are occurring together. Similarly, the second place also 0 and 1. But in a normal classical register, either 0 will be there or 1 will be there. So exactly one n bit will be there. But if you have a quantum n bit register, all possible strings, 2 power n possible strings are all 2 power n possible strings, you can put it in one n qubit register. That means you can store exponentially higher amount of information. If I am storing in a normal classical register, I am able to store only one n-bit string. But if it is a quantum n-bit register, I can store 2 power n. That is all possible n possible strings I can put there. Okay, so the quantum computers are evolving. This is the evolution. Now we have, see, in 1998 we have a small quantum computer with just 2 qubits. So it cannot do a lot of operations. So the technology is developing. There are no full-scale practical quantum computers existing now, but in the coming years, you will see a revolution in quantum computing. You will see better quantum computers emerging. Now, in this graph, you can see that these are the number of qubits. Say in 2020, around 128 qubits quantum computers. So they can be used for small calculations, but technology is developing. You will find fully functional practical quantum computers in the coming years. So IBM Quantum System 1 is a 27-bit quantum computer. So these are some of these figures. You can see some of the existing quantum computers. These are based upon the physics. So these computers look completely different from your PC or laptop. So what is a quantum threat to cryptography? So large general purpose quantum computers can exploit the quantum mechanical phenomena, right? So they can be used to solve mathematically hard problems, right? Many of the security systems are based upon hardness of solving certain mathematical problems. When quantum computers comes, these hard problems can be easily solved. And these crypto systems like RSA and difficult and key exchange, all these systems will become insecure. So this person, Peter Shor, came up with what we call classical algorithm. Classical algorithms are algorithms for normal classical computers. We have quantum algorithms meant for quantum computers. This man, Peter Shor, actually shocked the world. He came up with a quantum algorithm for factorizing large numbers, right? It is possible he came up with an algorithm which can run on a quantum computer. Now, unfortunately, we don't have a full-scale large quantum computer. But in the coming years, quantum computer will definitely come. So anyway, so two aspects are there. One is the mathematical or algorithmic research. Other is the hardware research, development of real practical quantum computers. The other aspect is developing algorithms for solving various problems using quantum computers. So Peter Shor came up with a quantum algorithm for quantum computers, which can be used to factorize large numbers very easily, as well as to find discrete logarithm. Right. So Shor algorithm, it is possible to break widely used RSA crypto system, Diffie-Hellman, elliptic cryptography, etc. Shor's algorithm fortunately requires 1000 qubit computer, a large. Fortunately, we don't have a 1000 qubit computer to break 160 bit. So it is there. The most of these crypto systems will actually can be broken in the coming years, because already algorithm is there. We are just waiting for the bigger quantum computers to come. So you can see in this graph the quantum algorithm, number of years it takes. Usually when the size of the number increases, the difficulty to factor or the time required to factor increases. The classical algorithms, the number of years will go up, but the quantum algorithm, which is a green graph, you can see that it is not. It is a moderate value only. So we can easily factorize large numbers or find discrete logarithms with the Shor's algorithm on a quantum computer. So if you want to factorize a 3-digit number on a classical with a trillions of hertz computer, it will take 1,50,000 years. On a quantum computer, it is going to take less than 1 second. So also this Low Grover, an Indian origin computer scientist, developed what is called a quantum computer algorithm, quantum algorithm for searching. An algorithm, a quantum algorithm, which can be run on a quantum computer, which can do searching much more faster than the searching. The searching means, suppose I have a list. I have a list of 100 people. I want to search for a particular person in that list. The normal way is you check whether the first person is that, second is that, third is that. It will take n steps. Or if 100 people are there, it will take 100 steps. But this Grover's quantum algorithm will take square root of 100, 10 steps only. In 10 steps, I can say that whether this person is there in the list of 100 or not. Right. So I have much faster way of searching. So the impact of this algorithm is that some symmetric algorithms like DES, AES can be broken much more faster using these kind of searching algorithm. But the main challenge of quantum computers is the challenge it gives to public key or asymmetric algorithms. Quantum computers, once they become widely in use, they are going to make all the computations faster. That means any security system or cryptographic systems you can break with lesser effort. So that means we need a stronger cryptographic algorithms. Cryptographic algorithms with large keys. So this is some comparison. If you use AES is a symmetric key cryptographic algorithm. If quantum computers, with the quantum computers, if you want to still need security, we need a much larger key. Currently AES uses 128 or 256 bits. Key length is 128 or 256. If we want to use it in the presence of quantum computers, we may require longer keys. SHA-2 is a hash function. Output length is, say for example, 256. This output length has to be much more higher in order to keep it still secure. RSA crypto systems, elliptical crypto systems, DSA, etc. All these will no longer be secure. So people are now thinking about what is called post-quantum cryptography. What happens? How do you make the system secure, or how do you do cryptography once powerful quantum computers come? So that is called actually post-quantum cryptography. So this, we said that we know that quantum mechanics or quantum physics is responsible for the insecurity to many of the crypto systems. Now people are actually using the principles of physics or quantum mechanics to design or develop cryptographic mechanisms. We have quantum mechanics based key exchange protocols. Since it is based on quantum mechanics, they are secure in front of quantum computer, right? So the post quantum cryptography, that is the cryptography after full-fledged establishment of quantum computing, is either you use principles of quantum mechanics to develop cryptographic systems, or there are certain mathematical mechanisms through which you can have secure crypto systems. See, RSA and elliptic curve, Diffie-Hellman, all these will not survive, but there are certain cryptographic constructions like elliptic, lattice-based cryptography, code-based cryptography, which may survive in front of a quantum computer, right? So, because see, why is the RSA or Diffie-Hellman, etc., become insecure is that we have quantum algorithms to solve factorization problem to break RSA crypto system. So try to come up with mathematical algorithms or crypto systems where it is not easy to find quantum algorithms. It is not easy to find algorithms which can run on quantum computers to break. Right. So this is a mathematical approach of having secure crypto systems in front of quantum computers. The other approach is use physics, use principles of quantum mechanics to develop cryptographic mechanisms. So I will stop here. So this is actually the I'll conclude here. So I will not go into the other slides. So the conclusion is that quantum computers or quantum mechanics is going to substantially area. It is going to make many of the existing algorithms insecure. So new cryptographic constructions based on either mathematics or principles of quantum mechanics have to be designed to make our world safe and secure. Okay, thank you. If you have any questions, you can quickly ask.
Thank you, sir, for the valuable session. Moving Before moving on to the QA session, participants, please note the link to submit the feedback form of the session is shared in the Meets chat. Kindly submit it without delay. Now the session is moving on to the Q&A session. If you have any doubts, grab this opportunity to make it clear.
Audience, please be free to ask your doubts.
Sir, I had a question.
Hmm.
Quantum computers, why is it taking so long to build? As in, like, what are the limitations of physics or real world that is making it so tough to build, sir, right now?
Right now, it is difficult to see the information is represented in using in photons or in electrons by looking at as spin of the electrons, right? So the thing is that it is very difficult to handle the quantum systems. The moment if you make any measurement or anything on a quantum system, it gets disturbed, right? So it is not like a representing information in a classical way where you keep something and put the other things together, stack them together, right? Quantum is you have to put this, say, photons together. Say, if I want to have n qubits, I need n photons. I have to put this n photons, right? These photons should not interact also with each other, right? So how do we actually do that? In classical world, it is easy. You one switch on, other switch off. If you have 10 switches, it corresponds to 10 registers. But in quantum world, this n position or n memory locations actually corresponds to n photons or n electrons, right? And this quantum world is very weird. That means there may be entanglement or mutual interaction between them, or if you look into that, or if you make a measurement, it gets disturbed. The information will be get disturbed, right? So it is practically very difficult to construct actually uh, full scale quantum computers. How do we have to keep these photons in our custody, right? So information is represented as state of the photons or state of the electron. So this photon or electrons will be manipulated physically on the basis of quantum laws to do the information processing. This is not very easy to experimentally do that.
Okay, sir. Thank you.
Sir, I have a question, if you don't mind. Sir, the quantum computer is it works with a non-binary system? It is working only in binary system, right?
Quantum computers use what is called a qubit, quantum bits.
Yeah.
Right.
Yeah.
Normal computers use bits, zeros and ones, but
Yeah.
quantum
Okay.
computers use a qubit. Qubit is actually a superposition of zeros and one. It will contain both 0 and 1. Right.
Okay.
So both information about 0 and 1. But just now I mentioned that if you measure a quantum thing, it will disturb. So if I have a photon, for example, it contains information about both 0 and 1. But the moment I measure it, it will boil down to, or it will collapse to one of these states like 0 or 1. Right. But
Okay.
as such, it will contain both information about 0 and 1. That is actually the advantage of quantum systems.
Okay. So can I work with an non-binary algorithm in a quantum computer? Means if I have an algorithm that is working on a ternary or quaternary number system, so is it working on a quantum computer?
Definitely.
Is it possible?
Any problem, theoretically, any problem can be solved using a quantum computer. Any problem.
Okay.
Any problem which is represented is just a representation of the number what you are seeing, right? So any problem
Yeah.
can be
Yeah.
solved, but the only thing is how to the algorithm you have to find out. For example, Peter Shor came up with an algorithm to factorize numbers. That is a quantum algorithm.
Okay.
Similarly, many of the problems you can try to find quantum algorithms. That is algorithms suitable for quantum computers.
Okay. Thank you, sir.
Any more questions?
Is there any other question? Jinsi?
I think no more questions.
Sir, if you don't mind, can I have your contact details so that if I have any doubt, I am working in cryptography, so if I have any doubt, I can contact.
Yeah,
If
you
you
can
don't
contact
mind.
me. Yeah, you can contact me, sure. If you go to the Digital University website, you can get all my details, email and other details you can get. You can mail to me. Okay.
Sir, I have a question.
Yeah.
Yeah, sir, what are the disadvantages with the existing post-quantum crypto systems? Say one has to come up with new crypto system, what things should be kept in mind?
If you are using mathematical principles, there is a chance that it can also get broken if a new quantum algorithm comes. Right. For example, people say that lattice cryptography, currently lattice cryptography is considered to be a post-quantum crypto system because there are no existing quantum algorithms to solve the problems or hard problems in lattice cryptography or to break lattice cryptography. But we cannot say that it is impossible to find quantum algorithms, right? So if you in post quantum cryptography, it is my feeling is that we have to depend upon principles of quantum mechanics, principles of not purely on mathematics but principles of physics to develop crypto systems, right? Which can be unbreakable, because whatever mathematical systems we develop, in future there is a possibility that they can be broken with newer quantum algorithms. Now there is a, you might have heard about machine learning. Now people are working on what is called quantum machine learning. Machine learning and artificial intelligence is mechanisms which can be employed on quantum computers, right? So these machine learning and artificial intelligence techniques also can be used for breaking security systems and crypto systems. So the purely mathematics based algorithms may not have much future. That is what I feel.
So, if someone comes up with a new crypto system, uh, say for example, multivariate, we have system of executions which is considered to be NPR. So, if someone comes up with an algorithm for that, even that crypto system is not.
Yeah, definitely, there is a possibility that quantum algorithms may come.
Okay. Thank you, sir.
But as long as quantum algorithms are not there, we can assume that they are safe. But we don't know how long they will survive. Even the security or crypto systems, there is nothing called perpetual or lifelong or security forever. So all the crypto systems we design for today will remain for a few years only. So mathematical constructions also you can do as long as there are no quantum algorithms. So their life depends upon how long the quantum algorithm, how long it will take people to design quantum algorithms to break them. So if it's a widely used cryptographic algorithms, then definitely there is a chance that quantum algorithms, people may come up with the quantum algorithms to break them. Or you have to find what are the limits of quantum algorithms in solving problems. You have to explore what are the limits, right? These quantum algorithms have exponential capabilities, but they may also have some limits, right? So if you can cross that limits in proposing crypto systems, mathematical crypto systems, then they will definitely survive.
So this is just a general question. So as far as I have seen, most of the post-quantum cryptography, crypto systems are based on, NP-hard problems. Are there any crypto systems that are not based on NP-hard but is still quantum resistant?
There maybe I'm not very familiar.
Okay.
Yeah.
Okay. So, in short, it's not based on NP-hard, but can we say this is not?
NP-hard is also a belief only, right? It doesn't
Yeah.
mean that it is going to be hard forever.
Okay.
And some crypto systems which are based on old crypto systems which are based on NP-hard problems also turned out to be insecure. So if you base a crypto system based on an NP-hard, that doesn't really mean that it is going to be secure forever. It can have other weaknesses also.
So what are other ways, we can make a crypto system if not NP-hard?
What are the other ways?
How we can come up with a new crypto system if not based on NP-hard?
The current mathematical approach is taking hard problems. That is the only approach we have. If you are looking at public key crypto, you mean about public key crypto systems, right?
Yeah.
Yeah, public key crypto systems. It is better to. That is the only current approach. Looking at NP hard problems or NP complete problems. But the point here is that that may not guarantee you always a secure crypto system.
Okay, that's all. Thank you, sir.
Thank you, audience, for your thoughtful questions, and thank you, Tony, sir, for your knowledgeable answers. Next, I would like to call Mr. Ranjit Verghese, Assistant Professor at Department of Mathematics, St. Thomas College.
Good evening, all. It has been such an honor to be a part of this wonderful event. On behalf of the organization, I would like to extend my heartfelt gratitude to our esteemed guest, Dr. Tony Thomas, Associate Dean and Associate Professor in Digital University of Kerala. Today we have had an opportunity to hear your thoughts, and this will surely be going to help in your understanding the cryptography and the related topics. I think in the words of Tony sir, the key thing that is the quantum information can't be copied or stored. Thank you for an enlightened and entertaining presentation on the topic, the quantum threat to cryptography. Thank you, sir. Thank you.
Thank you all.
Thank you, sir. Link for the next session is shared to the WhatsApp group. Please do join.